Okay, today we're going into 4.7, graphing linear functions, looking at functions in a new way. But before we do, this is a little warm-up quiz, and so we want to see that we can answer these successfully. So number one, state whether this is a direct variation or not. Number one, is that direct variation?
No.
No. Number two, is that direct variation?
Yes.
Okay, so when you transform those two equations so that y is isolated, you can see in this second one, we would end up with y equals negative x, and there is no y-intercept visible. Negative x, we could say, plus what? 0. So there is a y-intercept at 0, which is the definition of direct variation, right? When you transform this equation over here, number one, you actually have this constant, don't you? And so when you divide by what, negative 6, you would get negative 1/3 over there as a y-intercept. If you did transform it, you saw that. Number 3 and 4 are really the new concept from yesterday, and that is, can you write a direct variation equation for this little partnership here where y varies directly with x? So what did we say the model is for direct variation, everyone?
Y equals ax.
Okay, so you start with that when you see that we're asked to write a direct variation equation. And now, the one number that we need to fill in is for which variable here? A. We need to find A. So how do you find A in number 3? Tessa?
So plug in the x and y values.
Good. So we substitute 26 for y, and we substitute 2 for x, and we find A. It's the only unknown. And what is A?
13.
So good. She divided by 2, and A equals 13. So what is our answer?
Y equals 13.
Y equals 13x. Okay, so you must complete this by writing the equation. Y equals 13x. Okay, so how about question 4? What did you get, Chris?
Y equals 4.5.
Okay, so we found A. We reduced 4/18 to 2/9, and y equals 2/9 x is in the denominator. So a fraction is fine as A because, again, if we were to go graph this, A is our slope. So we know we would go up 2 and over 9. In this final section on graphing linear equations, we're going to use the same sort of graphing we've been using, which is mostly slope-intercept form. It's just that there is a different way we can look at a linear equation. So recall slope-intercept form. And let's say together, y equals
mx plus b.
Good. Okay, so we love that form. Sometimes especially in the real world, we want to compare things going on with graphs. So we might want to compare the sales of, if you were in business, the sales of iPads at the Apple Store versus the sales of iPads at Target or something like that. And we can show that really quickly in a graph. And it might be a linear graph. So we might actually put 2 lines on one graph, right? So if I have the sales at the Apple Store like this and the sales at Target like this, where is Apple earning more money? At the Apple Store, right? So they can anticipate that they're going to sell more there. I don't know if that would be a real true statement, but maybe it would on a brand new day where they're just releasing something, right? So when we have 2 linear equations on the same graph, we like to label them so people can understand. What does that mean? So we might label the Apple Store graph, we'll call that graph that line A, and the Target one we could call line T or something. Okay? So today we're going to learn about how you can name lines, and it's called function notation. Notation is a way to name stuff. Okay? So function notation for a linear equation looks like this. F of x equals mx plus b. We say, when we see f with x inside of parentheses just adjacent to it, we say f of x. The function f of x equals mx plus b. This right side looks really familiar, doesn't it? It's exactly like our slope-intercept form. So function notation basically is in slope-intercept form. It's just that instead of f of x, what do we have in slope-intercept form? Instead of f of x, over here we have y. So f of x equals y, really. It's a way to name a particular function. Any letter may be used to name a function. I might have a different one, like we just used, a of x, or t of x, g of x. In math textbooks, usually they start with f of x, and then they go g of x, h of x. They go kind of in that order. There are some letters we don't use often in math, like zero, like O, right? Because it looks like a 0. Or sometimes L, like a lowercase l just looks like a 1, so that's not a very good letter to use. And you'll see that one in cursive, right? So, okay, there are 3 things we can do with this. We can work with this in an equation in function form to find things we've already found before. And then we can graph an equation that's in this function form too. Okay? So first let's use function notation to find y. Take this down. What is the value of the function f of x equals 2x plus 12 when x equals negative 8? So has anyone found the value of this function when x equals negative 8? Or could anyone tell me how we could go about finding that? What do you think? What did we say f of x could be called? What did we just say? No? We said we love this form. Y equals mx plus b, right? So if I have this equation, f of x equals 2x plus 12, how could I rewrite this so it's more comfortable? Say it. Y equals 2x plus 12. We could write it that way, right? That's still true. We're going to find y if we only input this given x, right? So we can simply input negative 8 for x and find y. Find the value of the function when x is negative 8, right? So what is negative 16 plus 12?
Negative 4.
Good, negative 4. There it is. Okay? Everyone see? Now, we don't have to change from function notation to slope-intercept form. We can leave it in function notation, so please add this to your notes. Okay? So now we're being told what is the value of this function when x is negative 8. So we simply put the negative 8 in for x. On the left side now, we have a description of this function. You know, what will this function equal when we plug in negative 8? And over here we can start to simplify the expression. And again, negative 16 plus 12 is negative 4. So here's a statement we have if we leave this in function notation. And look at what we have. This statement, f when x is negative 8 equals negative 4, is really more detailed than this statement over here that just says y equals negative 4. Y equals negative 4 is true, but this statement over here tells us that when you input negative 8 into this function, you get out negative 4. It gives you a complete point, doesn't it?
Oh.
So this is one reason people use function notation. When you get to the bottom of simplifying this, you can see that negative 8 was the number that you input, and what came out of there was a negative 4. Negative 4, okay? I don't want you to be confused by function notation, but it is a bit confusing because we're so used to just y equals mx plus b. So as much as possible, use function notation in this assignment so you get more comfortable with it, okay? Here we have a function that's not named f, it's named h. So it's a different line. It's still a linear equation, isn't it? So we are asked to find the value of this function when x equals 7. And so let's do this in function notation. Okay, so Tatum, what do we do?
Plug in 7 for x.
So we say the function when x is 7 equals -7 times 7, right? And what is -7 times 7? So when x is 7, the function equals -49. And right in front of our eyes, we see a point on that line, don't we? We see a point at 7, -49. We could go graph that. Okay? Okay, if you're okay at this point, then let me complicate matters a tiny bit and ask you to use function notation to find x. Find x. So go ahead, jot this down and see what you can find. Okay, so in this case, we have a known value for f of x. So where does that get input here? For f of x, right? So the entire statement f of x equals 16. So now we can find x, right? Subtract 4 from both sides. 12 equals -2x. And when you divide by -2, yes, you do get x equals -6. That's true. So the number one mistake is when you're asked to find x, what do some people do with 16?
Plug it into x.
Plug it into x, that's right. And so the answer is -28. The wrong answer is -28 if you plugged in 16 for x. But that doesn't make sense, does it? Because you're finding x, so why would you plug 16 in for x? Do you see the problem there? Okay, please take this down. The nice thing about this section is we're at the very end of the chapter. This chapter was about graphing linear equations. So we weren't asked to write them, but we've been talking about writing them because we will do that in the next chapter. It's all about writing them. So when you are given a real world problem, they give you the beautiful gift right in the paragraph. They give you the equation. So there it is, right there, popping up. A bowling alley charges $5 to rent shoes and $4 per game. The cost after playing X games is given by this, 4x plus 5. Graph this and identify the range and domain. Graph it. Okay, so we weren't asked to find X. We weren't asked to find Y. We're asked to graph this. So this is something different. We haven't graphed an f of x type thing before. So we did say, though, what f of x equals. And f of x is another way of saying y, the output. So we can take and write this like this. Y equals 4x plus 5. And now we go graph that. Why don't we graph it using slope-intercept form, since that is faster than a table. But some of you have shown you're a little weak at that form still. So what does a person pull out of this equation that helps us graph? It is already in slope-intercept form. So what can you pull out of here? Anthony?
The slope.
Slope is?
4.
4. And the other thing you know is?
The y-intercept.
Y-intercept is? 5. Okay, so we want to make a quick graph. Okay, so we have slope, y-intercept form, and Anthony just pulled those two things out. Do we have a point? Which of these is the point? Is it the 4 or the 5, everyone?
5.
It's the 5, that's the y-intercept. Where do we find that on this graph? That's right, up 5, it's on the y-axis, that's why it's called a y-intercept. So we have the starting point, put it right up there at 5. It's our starting point. And now from that starting point, we travel using what? We use slope, right. And this slope says 4, but it's really 4 over what?
1.
1, because it's rise over run. As I look at my graph, I don't have a bunch of dashes above my 5. So I'm going to change this slope a little bit. It still must equal 4, right? But I want to go down 4. If I go down 4, then what will I have to do to the denominator? Make it negative as well. Does negative 4 over negative 1 equal 4? It does.
Oh.
So I'm going to go down 4, 1, 2, 3, 4, and over to the left 1. And I found the second point. Okay? Sometimes on tests, students worry when their y-intercept is so high. They're like, can I extend my graph way high? And I said, if you really want to. But you could go the other way if you change your slope to an equivalent form. But just going the other direction, right? Okay? And we could continue to go down 4 over 1 and draw your line. And if you're on paper, real straight, use a straight edge. Okay? Don't forget when you're asked this question to address that, right? So we need domain and we need range. What values, okay, this is a real world problem. So maybe our graph is a little bit extreme because, actually maybe it's really extreme. Why is our graph looking kind of extreme really? Wesley?
Because you can't like pay negative always for a game.
Okay, so really when we start at 5 here, this is what you would pay to rent shoes, right? You're paying to rent shoes. And so now we've gone, because of my love of not going high on this graph, we've gone to negative games, right? -1 game costs us $1. -1 game costs us $1.
Wow.
-2 games costs us, -3, they're paying us to not play games. Yay! Wow, we should go to the bowling alley, they're paying people today who don't play. I'm gonna not play a lot of games. Okay, no, we gotta go the other way, right? So what's the smallest value we may put in for x? What's the smallest value for x? 0. So we could actually rent shoes and not play. Okay, so there it is. X can be greater than or equal to 0, right? Have you ever done that, rented shoes and then didn't play? Do you think that somebody has?
Yes.
I bet it's happened, right? They got sick or they had to leave or whatever. Hopefully the bowling alley gave them their money back. But.
No, we rent shoes at the place.
Okay, so if the smallest x value is 0, and we plug 0 in here, what is the smallest y value? What's the smallest y value? 5. So, could the y's be greater than 5?
Yes.
And could the y's be equal to 5?
Yeah.
Yes. So there's your domain and range. So really, my graph needs to be a ray, right? Start here and go up. In reality, we don't go back in number of games. And there you go.